You are still able to see my screen?
Yes.
Good. So the last special type of equation we want to discuss is Legenda's equation. So as usual, we give the general structure of Legenda's equation and see how we obtain equation to such a differential equation. So a differential equation of the form one minus x squared y double prime minus 2x y prime plus n into n plus 1 y equals to 0 is known as Legenda's equation. So we can call it Legenda's differential equation or simply Legenda's equation. So if a differential equation takes that structure, then that's a Legenda equation. Let's go call this one beta. So equation beta may as well be written as d dx of 1 minus x squared dy dx plus where this n is supposed to be an integer. So solution to such an equation are called Legenda polynomials or Legenda functions. The solution of so just the same structure for the Bessel equation, whose solution is called Bessel function. Legenda equation solution are called Legenda functions. So the general solution. So given two independent solutions, Pn of x and Qn of x, the general solution y equals to a Pn of x plus b Qn of x. So that's how we write the general structure of the Legendre equation. Then in more general terms, Pn of x is given by -1 power half into n minus 1 n into n minus 1 n minus 2 then 2n minus 1 2n minus 3 2n minus 5 n plus 2 and then multiplied by 2 times 4 times 6 all the way up to n minus 1. And then multiplied by x, so which is called Legendre's function of the first kind. And then the more general form of Qn is given by n factorial divided by 1 times 3 times 5 times 2n plus 1 into x minus n minus 1 plus n plus 1, n plus 2, 2 times 2, n plus 3, x raised to power minus n minus 3. Okay, you don't have to be scared by the expressions for Q and P, because what we will ask you is to find the general structure. So the key thing is to show that the equation is already satisfying the standard form of the Legendre differential equation. So get your n value and write your answer involving this just arbitrary constants a and b, and then this is what you change now with the actual specific n value. The nitty-gritties on how to get the expanded forms for P and Q is really not necessary in this case, but it's always good to check how these expressions are obtained from the equation itself. So sometimes the Pn can be obtained from what we call Rodrigues formula. So Rodrigues formula enables us to find the Legendre polynomials Pn using Pn of x is given by 1 over 2 power n times n factorial, nth derivative of x, nth derivative of x squared minus 1 for n with respect to x. So all Legendre polynomials Pn can be generated from this contained formula, the so-called the Rodrigues formula. Pn of x is 1 over 2 power n times n factorial, then the nth derivative of the expression x squared minus 1 power n. So when n equals to 0, tell me the value of P naught. I know you're a trusted team. Where does n put 0
1.
and work out the solution? The answer will be
1.
1, correct. So because we are going to have 1 over 2 power 0, 0 factorial, d power 0, x power 0, x squared minus 1 power 0. So remember, the 0th derivative of a function is simply the function itself. And so when you say x squared minus 1 power 0, you get 1. So the function is 1. And 2 power 0 is 1. By default, 0 factorial is also 1. So you have 1 over 1 times 1, which is 1. So P naught is 1. What happens when n is 1? Replace n for 1 and tell me what would be the Legendre polynomial for that case.
Two x over 2.
2x over 2, which is the same as
X.
x, correct. And then when n is 2, at your own free time, confirm that P2 will be given by a half into 3x squared minus 1. So just write that at your own free time, you can confirm that. And when n is 3, the Legendre polynomial will be given by P3 of x is given by a half into 5x cubed minus 3x. So when n is 4, Legendre polynomial P4 will be 1 over 8 into 35x power 4 minus 30x power 2 plus 3. You can go on and define up to the n you like using that Rodriguez formula. So n equals to 5, P5 of x. When you work out, to confirm that it will give you 1 over 8, 63x power 5 minus 70x power 3 plus 15x etc. So that's how we can generate Legendre polynomials from the Rodriguez formula. So sometimes we may be asked to express a function in terms of the Legendre polynomials. So express f of x given by 2x plus 4 in terms of Legendre polynomials. So f of x given is a polynomial of which degree? Or the degree of that polynomial, f of x?
First degree.
First degree, correct. So here, f of x is a polynomial of degree 1. So we know that P naught is given by 1 and P1 is given by from the
X.
few polynomials we have calculated. What's the value of P1?
X.
X. So which means then our f of x will be given by 2, where this x I replaced by P1 of x, plus, remember 4 can be written as 4 times 1. So which is the same as 2 P1 of x plus 4 times P naught of x. So this will be the answer for that given function. So f of x given by 2x plus 4 in terms of the Legendre polynomials will be 2p1 plus 4p naught. Or another way of doing this, once you realize that your function is of degree 1, and in terms of the Legendre polynomials we have calculated, so when n is 0, we have a constant. N is 1, we have maximum power is 1. Of maximum power of x is 1. When n is 2, maximum power of x is 2. So when you're dealing the polynomial of degree 1, so it means that you are going to get linear combinations of the polynomials up to P1. If your polynomial was of degree 2, then you get linear combinations up to degree 3, up to P2. If the highest power of x in your polynomial is 3, then you carry out linear combination up to P3. This is what I mean. You will write f of x, which is given by 2x plus 4, is the same as a p1 a1 p1 of x plus a naught p naught of x, where a1 and a2 are a1 and a naught are constants to be found. So you'll say 2x plus 4 equals to a1. Then by definition from Roddick's formula, p1 is x. And from definition by Roddick's formula, p naught is given by 1. So this means we'll have 2x plus 4 equals to a1x plus a naught. And I think it's not hard to see that a naught is 4 and a1 is 2. Then you replace. So therefore, f of x is given by 2x plus 4, which is nothing but 2 p1 of x plus 4 p naught of x. So this is what you do. If you're given a quadratic function, you will get linear combination up to P2, because from the Roddick's formula, the highest power of x being 2 is in the P2 polynomial. And if you are given a cubic function and asked to express it in terms of the Legendre polynomials, you will do the linear combination up to P3. And so you have to know what is P1, what is P naught, and what is P2 and P3 set. Then you solve for the unknowns. If you are given a polynomial or a function of degree 4, then you'll get linear combinations up to P4, because from Roddick's formula, P4 is what gives us maximum power of x to be 4. And in a similar manner, you'll now, after getting the linear combination, simplify and compare coefficients. Then sometimes it will result into a system of linear equations, which you solve that system by the methods we discussed in engineering mathematics second year. So because of time, we need to be stopping. But just remember that similarly, just as was in the case of the Bessel function, we have recurrence relations involving the Legendre polynomials. For instance, if I have Pn, if I take n times Pn of x, I'll get 2n minus 1, and then multiplied by x, and then Pn minus 1 of x minus n minus 1, Pn minus 2 of x. Now, these recurrence formulas are very useful in that you may be asked to use the recurrence formula to generate other Legendre polynomials. For instance, you'll be told, given that this is true, find P2, P3, and say P4. Given further that P naught is given by 1 and P1 is given by X. So instead of the Rodriguez formula that generates the Legendre polynomials, you can use the recurrence formula to generate other Legendre polynomials. For instance, what we have in this case. And when you have such a case, you shouldn't miss the question because you can always manipulate this expression. So I'll say Pn of x, make it the subject, will be 2n minus 1 over n, and then times x, and then n minus 1 of x minus n minus 1 over n, p n minus 2 of x. I'm just rearranging the recurrence formula. So when we have to, so remember, if you have to apply a recurrence formula, then a solution at the term at a given position depends on the previous terms. So which means for us to get P2, then we need to be having an idea on the exact solution for P1 and P0. So that's why these two are given. So when n is 2, we'll have P2 of x equals to 2 by 2 minus 1 over 2, and then this thing you multiply by x, P2 minus 1 of x minus 2 minus 1 over 2, and then P2 minus 2 of x. We are simply replacing where there's n by 2. So what is 2 by 2 minus 1 over 2?
3 over 2.
3 over 2. So we are going to have 3 over 2. So P2 of x is going to be 3 over 2. And then 2 minus 1 is 1. And then 2 minus 1 is 1 over 2. And then P naught of x. And remember, P1 is given and also P naught is given. So where is, so remember there's an x here in the formula. This is an x. So this will be 3 over 2x. Then P1 is x. And then P naught is 1. So 3 over 2x times x gives first term will be 3 over 2 by 3 over 2x times x.
X squared.
X squared, and then minus a half. A half times 1 is a half, which is the same as a half into 3x squared minus 1, which is exactly the same thing we got from Rodriguez formula. So the thing is that you may be asked to generate Legendre polynomials either, say, from Rodriguez formula or from a recurrence relation. So now in a similar manner, once you have P2 and P1 will help you to get P3. So simply replace n for 3 in this equation and then replace appropriately the values. And to get P4, you replace n for 4 into the recurrence relation and then get the structure of the previous Legendre polynomials and substitute, simplify to get the answer. And remember, the answers should always agree with already what we have from the Rodriguez formula. So do as many examples as you can on the same. another key thing or another important thing that you should actually also check is the orthogonality of both basal functions and Legendre functions, and how to use recurrence formulas to generate Legendre polynomials. So with those many remarks, I wish to stop at that point. Then
Sure.